Good afternoon or good morning, depending on when you're watching this. We're going to go through 4 exponential functions, guided notes, and review. An exponential function is not a polynomial function. It is not a rational function. It's what we call a type of transcendental function. Transcendental functions transcend our normal basic algebraic functions like adding, subtracting, multiplying, dividing, powers, and roots. When I have an exponential function, which is a type of transcendental function, the variable is found in the exponent, not the base. Maybe we need to start and we need to identify we've got a base raised to an exponent. And we're going to say that if I simplify that, that would be equal to what we would call our argument. For example, if I had 2 cubed, 2 is the base, 3 is the exponent, and 8 is the argument, because 2 cubed simplified is equal to 8. All right. An exponential function shows patterns of growth or decay as you see an exponential increase or an exponential decrease. The inverse of an exponential function is a logarithmic function. All right, and then our mathematical definition. Mathematically, we define an exponential function, base a, as f of x is equal to a to the x power, where x and a are both real numbers. A has to be greater than 0, which means a needs to be positive, and a is not going to be equal to 1. So my base is going to be a positive value not equal to 1. A has to be not equal to 1, because if I do 1 to any exponent, that's my constant function, because 1 times 1 times 1 times 1, no matter how many times I do it, is just 1. It doesn't show growth or decay, so it doesn't follow my pattern for exponential functions. A has to be greater than 0, that keeps it positive. Otherwise, I could end up with an imaginary number. For example, if I had negative 3 to the 1/2 power, well, this negative 3 is a, that's my base. An exponent of 1/2, a fractional or rational exponent, tells me to take the root, so this 1/2 would be the square root of negative 3. That gives me an imaginary solution. Or it could end up to be something that is undefined. If it were 0, and I have maybe 0 to the negative 2, well, that negative exponent tells me to take the reciprocal of the base, which would put 1 over 0 squared, and that's an example of something that is undefined. Okay, so our exponential function is f of x equals a to the x, where our variable is in the exponent, and our base is going to be a positive number, not 1. Now, let's back up and think about how exponents work. We're going to kind of identify the pattern of the exponents. I want you guys to, well, you know what, we're going to do 2 to the power together, and then I'm going to pause the video and let you guys do 3 and 4 on your own. So we have a column of base 2, a column of base 3, and a column of base 4. Rather than starting with these negative exponent values, we're going to start down here. In fact, we're going to start with 2 to the first. 2 to the first is just 2. 2 squared would be 2 times 2, which is 4. 2 cubed is 8. 2 to the fourth is that 2 cubed times 2 again, so that's 16. Do you see a pattern forming? Hopefully you can see that each time I increase my exponent by 1, I'm multiplying by 2. Now I'm multiplying by 2 because 2 is my base. So I just changed my mind about exactly how we're doing this. If I move over here, 3 to the first is 3. 3 squared is 3 times 3, which is 9. 3 cubed would be 3 times 3 times 3, which is 27. So each time I'm multiplying by another 3 as the exponent increases, and I'm multiplying by 3 because that's the base. All right, so back to my 2's. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. If I want to finish the 3's here, 3 times 3 is 9, times 3 is 27, times 3 is 81, and then times 3 again is 3, and then 3 times is 243. Okay, now anything to the 0 power, do you know what that is? Well, some of you may. Let's develop it using our idea of a pattern. If we're increasing our exponent by 1, we're multiplying by 2. If we decrease our exponent by 1, what do we do instead of multiply? Well, when I'm going back the other direction, instead of multiplying by the base, I divide by the base. Where my base is 2, I start here and I divide by 2. 32 divided by 2 is 16, divided by 2 is 8, divided by 2 is 4, divided by 2 is 2. What is 2 divided by 2? Well, it's 1. Let's do our base 3. 243 divided by 3, because that's my base, is 81. Divided by 3 is 27. Divided by 3 is 9. Divided by 3 is 3. What is 3 divided by 3? Well, it is 1. That's one of my rules for exponents, that anything to the 0 power is going to give me 1. So 4 to the 0 is also going to be 1. That fits my pattern. All right, now let's look at those negative exponents and think about what that pattern would be. I'm trying to adjust my light a little bit to help you guys out. I don't know how successful I'm being. Remember, as we work our way up, we're dividing by the base. So we got 2 divided by 2 is 1. What is 1 divided by 2? Well, it's 1/2. What is 1/2 divided by 2? Well, 1/2 divided by 2 is the same thing as 1/2 times 1/2, which is 1/4. Do you start to see a pattern again? 2 to the first is 2. 2 to the negative 1 is 1/2. 2 squared is 4. 2 to the negative 2 is 1/4. So if 2 cubed is 8, what is 2 to the negative 3 going to be? Well, it's the reciprocal, 1/8. Because when I have a negative exponent, it tells me to take the reciprocal for the base. So this one is going to be 2 to the negative 4 is 1/2 to the 4th, which means it's 1/16. 2 to the negative 5 is 1/2 to the 5th, which is 1/32. And you can see how that pattern ties together the positive and negative exponents. All right, now I'm going to pause the video. I'm going to finish this page on mine, and I want you to finish yours and then start us back up. Okay, here we go again. Here is that first page completed. Hopefully your answers match mine and you were able to pick out those patterns for how our exponents work. Let's look at the next page of notes. Our rules for exponents. Now, we just talked about these rules for exponents and kind of discovered them together. Let's write them down. 0 exponent. Anything raised to the 0 power is 1. Anything raised to the 0 power is 1. So, for example, 3 to the 0 is 1. Negative 5 in parentheses to the 0 is 1. Anything, so any variable, I'm going to say m to the 0 power. Anything to the 0 power is 1. That's a general case. Then I have my negative exponent rule. The negative exponent, if I have a negative exponent, it tells me to take the reciprocal of the base. And we just saw that on the last page. So let's do a couple of these. When we did 3 to the negative 4, we said that was the same thing as 1/3 to the 4th, which is 1/81. Another example of a negative exponent, I'm gonna make the base the entire fraction and say negative 2/3 to the negative 2. Well, I need to take the reciprocal of the base. So I switch the base. My 2/3 becomes 3/2. When I switch the base, when I take the reciprocal, that negative goes away, but the exponent, the power that I need to raise it to, is still there. So I still need to square. It's just that my base flipped, and I end up with 9/4 because 3 squared is 9 and 2 squared is 4. What if I have a rational exponent? A rational exponent is the same thing as a fractional exponent. When I have a rational exponent, I'm going to take the root. When I take the root, the denominator of that exponent is the index of my radical, and the numerator of the exponent is the power of the radical. Now let's see what that looks like. Let's have 27 to the 2/3 power. 27 to the 2/3 power. Well, I have the base 27, and I have the exponent 2/3. The numerator is 2. That gives me the power, and the denominator is 3. That gives me the index of my radical. So I'm going to rewrite this as a radical with the radicand, the value underneath the radical, as the base, 27. This denominator tells me I'm taking the cube root, and the numerator says I need to square that. This is not a hard and fast order of operations, but it does simplify things nicely. You won't go wrong doing it this way. If I take the cube root of 27, I get 3, and then 3 squared is 9. If you don't remember how to take the cube root of something, remember, let's review the fact that if you've got the square root, you can do the inverse, the second function of that squared button on your calculator. If you want any other index, you do the inverse or second function button of that power button. So if I want the cube root, I would do second function power, and then it would give it to me there. So let's go ahead and input that. I would need the cube root, so I type 3, second function, and then my power button. And then I input the radicand, hit enter, and that tells me that the cube root of 27 is 3. Okay, let's practice these by evaluating each exponential function. F of x equals 4 to the x. I know this is an exponential function because the variable is in the exponent. So on f of 3, I want to evaluate 4 cubed because I replace the x with 3. Well, we already did this one. 4 cubed is actually 64. What if I replace my exponent x with -2? In this case, I would have 4 to the -2. My rules say that negative exponents tell me to take the reciprocal, so that's 1 over 4 still squared, so 1/16. What if my exponent needs to be 3/2? Well, 4 to the 3/2 equals, I have a radical. 4 is the base, the denominator is 2, so it's the square root, and then I'm going to cube that. Square root of 4 is 2, and 2 cubed is 8. All right, the next one is just a little more complex, but we can handle that. I have g of x is my function, my base is 5, my exponent is 2 minus x. And then these are the values I'm going to plug in for x. So for the first one, g of 3 becomes 5 to the 2 minus 3. Well, 5 to the 2 minus 3 is 5 to the -1, and that negative tells me to take the reciprocal of the base. So I have 1/5. What if I need to plug in -2 for x here? Well, that's 5 to the 2 minus -2, because it starts as 2 minus x. 2 minus -2 is the same thing as 5. 2 plus 2, which is 5 to the 4th. And 5 to the 4th is 625. Feel free to use your calculator for that. Our third example, h of x equals 1/3 to the x. I have a fraction as my base. That's fine. My base has to be positive and not 1. It meets those requirements. So for the first one, I have 1/3 to the -2 power. That negative tells me to flip my base, take the reciprocal of the base. 3 over 1 is just 3, so I have 3 squared, which is 9. The last one here tells me to replace my variable with 3. So I have 1/3 cubed. 1 cubed is just 1. 3 cubed is 27. As always, I would want to simplify anything that I could. Okay, the next page of our notes, we're going to start talking about graphing exponential functions. Now, when I graph exponential functions, remember our definition for an exponential function, f of x equals a to the x for all values of a greater than 0 and not 1. Those are the restrictions I put on the base. A is the base. It is not the domain and range of the function. I'm not putting any limits on what my exponent can be. My exponent can be any real number. So from -infinity to +infinity is my domain. The range is going to be limited by a horizontal asymptote. And we all know what asymptotes are from rational functions. So the range is going to be limited by horizontal asymptote. And where that horizontal asymptote falls depends on my graph. Pattern of transformations that you have known since we began this semester is the same pattern of transformations we're doing here. It's the same as the pattern of transformations for polynomial functions. If I put a negative out in front, that would tell me that my function reflects across the x-axis. Where I have x minus h that goes up into my exponent, that is still my horizontal shift. And it goes the way, you know, it goes going to go the opposite way. So if this was x minus 2, it would move my function 2 to the right. And finally, I have that plus k tacked on at the end. This is still my vertical shift, either up or down. And because it's plus k, it goes the way we expect it to go. All right, we're going to choose a base. Any base will work as long as it's positive and not 1. And that is what we're going to call our parent function. Our most basic function of that base is our parent function. So we are going to graph as our parent function f of x equals 3 to the x. My base is 3. Now we know because this is an exponential function, I can use any value I want to for x. My domain is all real numbers. In general, when you're starting with your parent function, no matter what the base, you want to plug in 5 basic values for your exponent. We're going to do -2, -1, 0, 1, and 2. Those are my 5 standard values that if I plug in, they're going to show me where that exponential increase or exponential decrease shows up. So we have the shape of our graph. Okay, 3 to the -2. Let me put some lines in here so that maybe we can kind of separate out our points. If we do 3 to the -2, f of x equals 3 to the x. 3 to the -2, that negative test to take the reciprocal, that's 1/9. -1, 3 to the -1 is 1/3. Anything to the 0 power is 1. 3 to the first is 3, and 3 squared is 9. So those are my y values, my function values for these x values. Let's put that on the graph. Okay, 3 to the -2, where x is -2, it is positive 1/9. That is just barely above my x-axis, and then it goes up a little more. When x is 0, y is 1. That's my y-intercept. Where x is 1, y is 3. I start to see my exponential increase. Where x is 2, y is 9. 3, 4, 5, 6, 7, 8, 9 is going to be about right there. So I have this, if I kept going toward the left, my fractions would get smaller and smaller. If I keep going to the right, my curve is going to get steeper and steeper as it travels up. You see that I have a horizontal asymptote at 0. That is my limit on my range. Horizontal asymptote at y equals 0. Because if I did -3, that would be 1/27, 1/81, and that this fraction just gets smaller and smaller as I move out. My line gets closer and closer to that horizontal asymptote, that value of 0. So that is my horizontal asymptote. My y-intercept is my point that I'm going to focus on shifting as I do some transformations. This is my parent function. That's my basic shape of an exponential function. If my base is smaller, if it's 2, it doesn't increase quite as quickly, but it still looks like this. If it were 5, it would shoot up a lot faster. It would be really steep. All right, let's think about these transformations. For g of x equals x, 3 to the x plus 2. Well, we already know that my parent function is right here. My parent function, f of x, equals 3 to the x. It goes through that point 0, 1, and it has a horizontal asymptote at y equals 0, so that is my parent function. Well, what about this transformed function g of x? What's my transformation? Well, my transformation is happening in the variable, so it's a horizontal shift. It is going to, for x plus 2, that shifts to the left 2 units. Left 2 shifts left 2 units. Okay? That means I'm going to take this point and I'm going to shift it to the left 2 units, and it's right there. I didn't go up or down, so I didn't move my horizontal asymptote. So my function is going to look like this, the exact same shape, just shifted to the left. My domain is still all real numbers. My range is still from 0 to infinity. Let's go ahead and write that in up here. My range is going to be from, oh, not inclusive. Curve, curve, curve. Not inclusive because it never gets there. 0 to infinity. My range here is still 0 to infinity. Domain is always going to be all real numbers. Okay, now let's go back and we're going to think about our parent function again. F of x equals 3 to the x. Right there. F of x equals 3 to the x. And then we look at our transformed function, h of x. This time I've got plus 2, but not in the exponent. It's just tacked on at the end. That is going to be a vertical transformation. And that is going to shift my function 2 units down. Not down, I'm so sorry. 2 units up. That's going to shift my function 2 units up. So I'm going to take this y-intercept and I'm going to move it up 2. I'm also going to take this horizontal asymptote that was at 0 on the last function, but it needs to move up 2. It was at 0. Now it's not up here at 3 where my intercept moved. It's at 2. So my horizontal asymptote is at y equals 2. For this one, my horizontal asymptote was at y equals 0. Now it's at y equals 2. Okay. So for this function, I didn't finish drawing it. For this function, my transformed function, same shape, just shifts up. For this function, my domain is still all real numbers, but my range has changed. It's shifted up 2. Instead of from 0 to infinity, now my range is 2 to infinity. Now my range is 2 to infinity. All right, one more transformation we're going to talk about together here. M of x equals negative 3 to the x. Remember we said when we have a negative out front, it reflects it across the x-axis. So it's going to flip it upside down. Parent function first. Parent function, f of x equals 3 to the x. Transformed function, m of x equals negative 3 to the x. That is going to reflect it across the x-axis. So instead of when I just reflect it, when I flip it, that horizontal asymptote is on the x-axis. It doesn't change. My intercept that was 0, 1 is now 0, negative 1. So instead of an exponential increase, my graph shows an exponential decrease. So domain is still all real numbers. Range is I flipped my range. Range is from negative infinity up to 0. That's the high value of the range. And instead of an exponential increase like my parent function, I have an exponential decrease. Okay. Now we're going to talk about our natural base. Take a second and read these paragraphs and then we'll go through them together.